I want you to try something for me right now. Don't worry, you don't have to move or anything. Just listen to this sentence. The old man, the boats.
The old man, the boats.
Right. Now, when you first heard the old man, your brain probably painted a picture of an elderly guy, right?
Like sitting on a park bench or something.
Exactly. But then you hit the word boats at the very end, and suddenly your brain has to just scramble.
Right. You realize man isn't a noun here.
It's a verb. The old people are manning the boats.
That's a classic garden path sentence. It leads you down one path.
Yeah.
And then it forces you to backtrack.
But here's the thing that really struck me in our sources for this deep dive. To even experience that confusion, you have to be holding the beginning of the sentence in your head while you process the end.
You're knitting time together.
Yes, we take that totally for granted. But for decades in AI, that simple act of just holding on was effectively impossible.
It really was. I mean, we spent a long time building machines that we're brilliant at now, like a convolutional neural network, the kind that recognizes faces in your photos. It's amazing, but it lives in the state of frozen time.
Frozen time? I mean, that sounds like a sci-fi horror trope.
It's not far off. Imagine if you woke up every single second with total amnesia.
Oh, wow.
You see a frame of video, you process it, and then poof, gone.
Right.
The next frame arrives, and you are meeting the world for the very first time again.
So it's a goldfish.
That was AI for a long time. It was a goldfish meeting. Every input, like, it was brand new.
And you can't understand a conversation if you're a goldfish.
Yeah.
You can't predict the stock market. You can't write a novel if you don't know what happened literally 5 seconds ago.
Which brings us to the topic of this deep dive.
A machine that remembered.
Exactly. We're unpacking recurrent neural networks, RNNs.
Our mission today is to figure out how engineers finally gave AI a timeline, how they taught machines that what came before actually matters for what comes next.
And it's a fascinating engineering story because it taught us how difficult memory actually is to build. It's not just about, throwing things on a hard drive.
Right. It's about deciding what to keep.
What to ignore, and how to carry a thought forward without letting it just degrade into static.
So let's get into it. Let's look at part one here. We have these stateless networks, the goldfish. They take an input, do some math, give an output, boom, done. Why is that bad for language?
Well, the problem with the goldfish is that it assumes every input is independent.
Okay.
But in the real world, data is rarely independent. Order is everything.
Like the classic example, the dog bites the man versus the man bites the dog.
Right. Same exact ingredients. If you put those words in a bag and shake it up, the contents are identical. But the sequence dictates who's going to the hospital.
Or think about music. You can't just smash C, E, and G together and say, hey, I wrote a song.
No, you just played a chord. A melody is defined by the interval, the sequence between the notes, play them backward, and the whole feeling changes.
So if I ask a stateless network, the capital of France is blank.
It sees the word is and just blanks out. It has no idea you said France 2 seconds ago. It needs state.
It's so frustrating to even think about.
Yeah.
Trying to talk to something that forgets what you said 5 seconds ago. So how do we fix it? How do we build this state?
The secret is startlingly simple. It's a loop.
A loop.
The breakthrough was the recurrent part of the name. In a standard feed-forward network, information moves in a straight line. Input, hidden layer, output.
Right.
But in an RNN, the output of the hidden layer isn't just set forward, it's copied and it's fed back into itself.
So it becomes an input for the next step.
Exactly. It feeds on its own task.
Our sources use a really great analogy for this. Imagine you were sitting in a massive lecture hall taking notes.
Right, the lecture analogy. Think about what you're actually doing in that room. You don't just write down the exact word you hear right now in isolation.
No, I'd have a page of random words.
You combine the current word you're hearing with the notes you've taken so far. You use both to update your overall understanding of the topic.
So the current input is the new word the professor just said.
And the hidden state is your accumulated notes, your memory.
Okay, so let's visualize this. The sources talk about unrolling the loop. What does that mean?
Unrolling is how computer scientists visualize this process over time. Imagine it like a relay race.
Okay, I'm picturing a track.
You've got a line of runners. Runner 1 gets the first word of the sentence, they process it, and they hand a baton to runner 2.
But this isn't a normal baton, is it?
No, this baton is the hidden state. It's a vector, a string of numbers that carries the history of runner 1.
So runner 2 takes that baton, adds their own energy, the second word, and passes it to runner 3.
Yes. And by the end of the sentence, that baton is supposed to carry the history of every single runner who touched it.
Supposed to. That feels like a very load-bearing supposed to.
It is, because this is where the cracks begin to show. This is the bottleneck.
All right, because this baton, this hidden state vector, it's not infinitely huge.
No, it's a fixed size. Let's say it's just a specific list of 512 numbers.
Wait, so if I read a short sentence like, hello there, or if I read the entire text of War and Peace, the container for the memory is exactly the same size.
That is the constraint. It's incredibly stressful for the network. After 100 words, the RNN has to cram everything important into that same small vector.
It's like trying to summarize a massive, epic fantasy novel into a single tweet.
You get the gist, right? Like, angry guy on a boat goes home, but you lose the nuance. You lose the detail.
And if you lose the details, the whole system kind of breaks down on long sentences.
Which leads us to the most infamous problem in early AI, the vanishing gradient.
Yes, the vanishing gradient. Let's look at this sentence from the source material. I grew up in France, then there's a bunch of filler text, maybe a whole paragraph, and it ends with, I speak fluent blank.
To fill in that blank with French, the AI needs the memory of the word France from way back at the beginning.
But it's been passing that baton for 100 steps.
Right. It's a game of telephone.
I whisper to you, you whisper to the next person, and by the end, France turns into pants.
Exactly. And mathematically, the reason this happens is because at every step, the network multiplies the signal by a small decimal.
Ah, right. And if you multiply 0.5 by 0.5...
You get 0.25, do it 100 times, and your signal is basically zero. It's washed out in the noise. The connection between France and French just vanishes.
The machine literally forgets how the sentence started. So it's 1997. AI has hit a wall. How do we fix the vanishing gradient?
Two researchers, Sepp Hochreiter and Jürgen Schmidhuber, introduce a revolution, the LSTM.
Long short-term memory, which is such a beautifully contradictory name.
It tells you exactly what it does, though. It makes the short-term memory, the hidden state, last for a long time.
Okay, so the standard RNN was this chaotic relay race, or like a rushing river where everything just gets swept along and mixed together.
Right, the rushing river. The LSTM is fundamentally different. It's an engineered canal system. It has locks and dams.
The gates.
Yes, the gates. Instead of just blindly mixing new words into the memory, an LSTM cell has the ability to choose.
It's a bureaucracy. Our sources break this down using a really great analogy of cleaning out a closet. We've got 3 gates. First up, the forget gate.
The trash can. It looks at the existing memory and says, is this stuff still relevant?
So if the paragraph moves from talking about a dog to talking about a car, the forget gate decides to toss out the dog stuff. We don't need it.
Exactly. Next is the input gate. You're at the store buying new clothes for the closet. It looks at the new word and decides, is this actually important?
Because if I say the dog, you only really need to keep dog.
It filters the noise,
Yeah.
and then you have the output gate. Deciding what to wear today out of everything in the closet. What part of my memory is relevant for predicting the very next word?
But the real magic here, the thing that fixes the game of telephone, is the cell state.
The superhighway.
Right. It's this protected lane running through the top of the network.
And here's the crucial math difference. Updates to this highway are additive, not multiplicative.
So the signal doesn't vanish.
Right. 1 + 1 is 2. The word France gets on the highway at step 1, cruises right past 100 filler words completely untouched, and gets off at the exit ramp right when it needs to predict French.
That is just brilliant. And the sources briefly mentioned the GRU as well.
Yeah, gated recurrent units. It's basically a simplified LSTM. If an LSTM is a complex Swiss watch, a GRU is a digital watch. Fewer moving parts, but still keeps great time.
So we solved the memory degradation. We can read a long sentence. But there's another problem if we're trying to actually understand language, right? Reading left to right isn't always enough.
It's not.
Think about this sentence. The blank ate the cheese.
If you pause at the blank, you have no idea. Is it a man, a dog, a mouse?
But if I give you the end ate the cheese, you instantly know it's probably a mouse. You need the future to understand the past.
Which gave rise to bidirectional RNNs.
It's like reading a mystery novel.
Yes. You read forward to get the setup, but you also have to read backward to catch all the clues you missed.
So they literally just run 2 networks.
2 networks. One reads left to right, one reads right to left, and they combine their notes. It gives the AI a full panoramic view of the sentence.
And this panoramic view leads to what might be the coolest application of the source material, the translator.
Sequence is sequence.
This was the tech behind that massive Google Translate upgrade back in 2016, right? Before this, machine translation was Rough.
It was word-for-word substitution. You'd feed it an English idiom, and it would output total nonsense in French. Secret changed the game by acting like a United Nations interpreter.
Okay, break that down for me.
It splits the job into two parts, the encoder and the decoder.
So the encoder is the listener.
Right. The encoder listens to the English sentence. It just sits there, taking in the words one by one, updating its hidden state. It doesn't speak a word.
It's just building a mental model.
And when the sentence is finished, the encoder produces one final vector, the thought vector.
Wait, so it compresses the pure abstract meaning of the entire sentence into one single list of numbers.
That's the idea. And then it hands that thought vector over to the decoder.
And the decoder's job is to speak.
It takes that pure meaning and unfolds it into French or Japanese or whatever language you want.
That sounds incredibly elegant, but also kind of terrifying. You're cramming an entire complex thought into one vector.
You're right to be terrified. The bottleneck strikes again.
If that thought vector is even slightly off, the entire translation is doomed.
Exactly. And that pressure, that fundamental limitation of having to process things one step at a time and compress them, is actually what led to the end of the RNN era.
The shift to transformers.
Right. RNNs are sequential. Step 2 cannot happen until step 1 is done. You can't speed it up.
Like the old saying, you can't get 9 women to make a baby in 1 month.
Exactly. But tech companies wanted to train AI on the entire internet. Doing that one word at a time would take forever. Transformers process everything in parallel.
They look at the whole sentence at once.
Using attention. They don't need a hidden state baton because they can just look directly back at the word France whenever they want.
So does that mean the machine that remembered is just a museum piece now?
No, not at all. RNNs are still used for time series data, predicting weather, things that genuinely happen in strict sequence. But more importantly, their legacy is foundational.
They taught us what to look for.
They got AI that it needs a state. They taught us the value of forgetting things with gates. And the flaws of the RNN, that compression bottleneck, is exactly what motivated the invention of attention.
We moved from a machine frozen in time to a machine carrying a baton of memory. It's a huge leap.
It changed everything.
You know, reading through all this, the mechanics of the hidden state, I couldn't help but feel a really weird, almost philosophical kinship with the RNN.
How so?
Well, the big limitation of the RNN is that it tries to compress its whole life story, its whole history, into a single fixed vector.
Right, the bottleneck.
But isn't that what we do? I mean, right now, as you and I are having this conversation, I am not actively remembering every breakfast I've ever eaten or every conversation I had in high school.
No, you're operating on a highly compressed summary of yourself.
I am the current hidden state of my own life. I'm carrying this baton that's been painted over and chipped and modified by decades of sequence.
And just like the vanishing gradient, sometimes the signal from your childhood gets weak. You know it shaped your vector, but you can't quite read the original input anymore.
We're all just walking, breathing RNNs, trying to predict the next word without losing the plot.
And hopefully our forget gates are working, because you really don't want to carry everything.
No, you don't. That is both terrifying and deeply comforting. Thank you so much for walking us through the machinery of memory today.
It was my pleasure.
And to everyone listening, notice the sequence of your day today. Because once the moment passes, all you have left is the vector. We'll see you in the next deep dive.